In this research paper, the authors introduce a novel optimization framework for Bayesian meta-learning, which is cognizant of trustworthy uncertainty quantification. The proposed method, trust Bayes, aims to minimize an objective function j, m, k, while ensuring that the ground truth of the function phi, x, can be captured by intervals I m, k, x, and e, m, k, x, with a pre-specified probability at least 1 delta. The optimization problem is formulated as a minimization of j, m, k, subject to constraints on trustworthy uncertainty quantification. The paper begins by discussing the importance of uncertainty quantification in engineering systems operating in the real world, such as autonomous cars and unmanned aerial robots. It highlights the limitations of existing Bayesian learning methods, including the need for accurate prior and likelihood functions, and the potential for large intervals when using Gaussian processes or Bayesian neural networks. The authors then define the problem of Bayesian regression with trustworthy uncertainty quantification, where the goal is to identify prior mean and covariance functions that minimize the objective function j, m, k, and capture the ground truth phi, x, with a pre-specified probability. They also introduce a meta-dataset dmeta containing observations of functions phi, which can be used to estimate and optimize j, m, k, and the constraints on trustworthy uncertainty quantification. The paper proposes Trust Bayes, a novel optimization framework for Bayesian meta-learning that is cognizant of trustworthy uncertainty quantification. This framework does not require explicit assumptions on the prior model or distribution of the functions, and it uses the meta-dataset dmeta to optimize the objective function and constraints. The authors also provide a mathematical formulation of the optimization problem and discuss its motivation in the context of safe learning and exploration. In addition to proposing the Trust Bayes framework, the authors analyze the lower bounds of the probabilities of the ground truth being captured by the specified intervals and analyze the sample complexity with respect to the feasible probability for trustworthy uncertainty quantification. They conduct a case study using Gaussian process regression for verification and comparison with the metaprior algorithm. Overall, this paper presents a novel approach to Bayesian meta-learning that prioritizes trustworthy uncertainty quantification without explicit prior assumptions on the model or distribution of the functions. It contributes to the development of more reliable and efficient machine learning models for real-world applications, particularly in engineering systems that require high autonomy and safety. The Trust Bayes framework is introduced to solve the problem of estimating the confidence intervals for the predictions of a machine learning model. This framework leverages empirical estimates from a metadataset, dmeta, and utilizes properties of sub-Gaussian random variables to derive lower bounds for the probabilities of a function phi falling within the confidence intervals I theta, phi, x, and e, theta, phi, x. These lower bounds are then used to approximate the original optimization problem with a more tractable form, which can be solved numerically. The framework also provides a sample complexity for the lower bound of feasible delta, indicating that the freedom of selecting delta can be increased by increasing the sample sizes t, eval and n. The proof of theorem 3.1, which characterizes the lower bounds for expectations C1 and C2, is based on the properties of sub-Gaussian random variables and Hoeffding's inequality. The theorem's results are used to estimate the probabilities phi, x, element of I theta, phi, x, and phi, x, element of E, theta, phi, x, and to approximate the original optimization problem. The sample complexity for the lower bound of feasible delta is also discussed, showing how it can be improved by increasing the sample sizes t, eval and n. This research paper focuses on trustworthy uncertainty quantification in Bayesian regression problems. The authors formulate trustworthy uncertainty quantification as constraints on capturing the ground truths of the function by intervals depending on the prior and posterior distributions with a pre-specified probability. They propose Trust Bayes, a Bayesian metalearning framework that is cognizant of trustworthy uncertainty quantification without explicit assumptions on the model, distribution of the functions. The authors characterize the lower bounds of the probabilities of the ground truth being captured by the specified intervals in terms of the empirical estimates and analyze the sample complexity with respect to the feasible pre-specified probability for trustworthy uncertainty quantification. They also provide a case study using Gaussian process regression, GPR, to verify the proposed framework and demonstrate the necessity of trust Bayes for trustworthy uncertainty quantification when the prior is not necessarily correctly specified. In the case study, the authors use GPR as the algorithm alg and consider a specific prior predictive distribution and posterior predictive distribution. They experiment with a dataset of 2,000 functions, each with 20 inputs and 100 outputs, and evaluate the performance of trust Bayes and a baseline method called metaprior. The results show that trust Bayes outperforms metaprior in terms of the empirical estimates of the probabilities of the ground truth being captured by the specified intervals and the mean squared error, MSE, of the posterior predictions. The authors also provide visual comparisons of the prior and posterior predictions using trust Bayes and metaprior, which demonstrate that trust Bayes is able to capture the values of the functions with larger variation. The paper concludes by highlighting the importance of trustworthy uncertainty quantification in Bayesian regression problems and the effectiveness of trust Bayes in achieving this goal. The research paper discusses the application of Bayesian methods in machine learning, focusing on metalearning and its implications for safe online learning. It presents a comprehensive comparison between trust Bayes and metaprior methods, highlighting their differences in posterior predictions over sample functions. The authors emphasize the importance of ensuring safety in learning algorithms, particularly in dynamical systems, and discuss various approaches to achieve this, such as region of attraction estimation and Bayesian optimization with safety constraints. The paper also touches on model-agnostic metalearning and its generalization capabilities, including the use of shallow Bayesian metalearning for real-world few-shot recognition. Throughout the discussion, the authors stress the need for provable guarantees for generalization and the importance of understanding the underlying dynamics of the systems being learned.